All right, guys, we're going to do a quick recap from yesterday where we covered calculating average atomic mass. So let's look at this problem. Here it says we have magnesium that has 3 naturally occurring isotopes. So remember, we're going to have a problem for each isotope. It tells us that 78.70% of magnesium atoms exist as magnesium 24, which is a mass of 73.985 grams. So remember, we're doing for each isotope, I'm going to do just magnesium 24. That way I can keep them separated. We're doing the mass, the 23.9850 times the percent written as a decimal. So that 78.70% becomes 0.7870. So when we put that in the calculator, that isotope has a relative mass of 18.876. We'll keep several decimal places on there. For the next isotope, we have 10.03% exist as magnesium 25, which has a mass of 24.9858. So yet again, we do the mass times the percentage changed into a decimal. So make sure we move it 2 places. So that'd be 0.1003. That isotope is going to have a relative mass of 2.506 AMUs. And then we're going to do the same thing for magnesium 26, which has a mass of 25.9826. Multiply that by the percentage, the 11.17, but move the decimal twice, so 0.1117. So that isotope has a relative mass of 2.902 AMUs. So we have the relative masses of each isotope. Our last step is going to be to add those together. So 18.876 plus 2.506 plus 2.902. We get a relative mass of 24, or excuse me, an average atomic mass of 24.284. And remember, our unit for average atomic mass is AMUs. And remember, you can check yourself. It told us this is magnesium. Magnesium on the periodic table is 24.31. Our answer is relatively close to that. So we are on the right track. But remember, you have to show the work and show the step for this. All right, so we are going to switch gears slightly and go through nuclear decay. We talked about how, every atom has a set number of like protons, neutrons, electrons. Some of these are too large to hold themselves together and they're unstable and they will break down over time. So that leads us into radioactivity. This is the process in which one of those unstable atomic nucleus emits charged particles and energy. So the nucleus that's unstable or too big to hold itself together will break down into 2 smaller nuclei, or it'll give off particles to become smaller. And it will do this until it becomes a stable isotope. Radioactivity is also referring to the penetrating rays and particles emitted by a radioactive source. So just that it has the ability to give off that energy. We refer to these unstable nuclei as radioisotopes or radioactive isotopes. This is any atom containing an unstable nucleus. So since it is unstable, it has to break down to become stable. And these isotopes are the source of all radioactivity. So it's simply that particle is too large to hold itself together and it's unstable. Some common radioisotopes, and we have these around us on a daily basis. But some common ones that you may have been exposed to before, uranium-238. That's what is used in some of our nuclear power plants. They use it in warheads, things like that. One that you've probably heard of before is the carbon-14. That was used for the radiocarbon dating in biology. So unstable isotopes can spontaneously change into other isotopes over time through nuclear decay. So you don't need a power source to make this break down. It will just naturally break down over time. And what happens is during nuclear decay, atoms of one element can change into atoms of a different element altogether. So we can actually change from one element into another and change the chemical composition or the chemical makeup of our atoms. And we're going to look at how this works and what particles are given off. But for example, that uranium-238, that's used in nuclear plants and warheads, that will break down and change into thorium-234. So it will make a whole new element whenever it breaks down. This breakdown is done by losing or sharing any type of particle or energy in general. So we're going to talk about they typically lose protons, neutrons, and electrons, depending on what change is occurring at that point in time. So looking at nuclear radiation, without you kind of knowing it or being aware of it, we are exposed to nuclear radiation on a daily basis. There are radioactive isotopes in the soil and material around us daily. So we are constantly being exposed to that energy that is being given off. But it is what we refer to as background radiation. This radiation occurs naturally in the environment, but it is at lower levels. So this is going to come from radioisotopes in the Earth's materials, trace amounts of radioactive elements or minerals that are going to be around you, and cosmic rays, so rays from the sun. Cosmic rays are going to be streams of charged particles from outer space. So a lot of this is with sunlight. We're going to gain some of that energy, some of that heat. And it sounds scary that you are exposed to radiation. But like I said, this is a background level, so it's a lower level. So the levels are low enough to be safe. Now, of course, if you have exposure 24 hours a day, 7 days a week for years on end, it could possibly do damage. But it's at such a low level that it can't really penetrate into your cells to cause damage. With nuclear decay, there's two main types of nuclear decay. Everything is either classified as fission or fusion. So fission is the splitting of an atomic nucleus into two smaller parts. So fission is splitting apart. In nuclear fission, tremendous amounts of energy can be produced from a very small amount of mass, because this does create kind of a chain reaction. So you can see the picture now at the bottom. There is a nucleus of uranium-235 that gets hit with a neutron, making it more unstable than it is. So that causes it to split into two new nuclei. Well, whenever it splits, it gives off neutrons as well, which when they come in contact with another uranium-235, that one will split. So one atom splitting is going to set off a reaction to cause more atoms to split. Those will set off a reaction to cause even more to split. So this is going to be a continuous reaction that's going on. And then the other type we deal with is fusion. Fusion is the process by which the nuclei of two atoms combine to form a larger nucleus. Excuse me. So we said fission was splitting, fusion is combining. Fusion actually produces more energy than fission does, but it is not as common for us around here. Our nuclear power plants and stuff are fission reactors instead of fusion reactors. Fusion is what actually powers the sun and the stars. It's the fusion of hydrogen atoms into helium atoms. Now, the reason we don't typically use these, even though they produce more energy, is these reactions require very high temperatures where matter exists as plasma. It's a state of matter where atoms have been stripped of their electrons, so it will have a charge. Because this has to be at such high temperatures, we cannot maintain it on Earth. So scientists have not been able to make a fusion reactor due to the high temperatures that would be needed. I believe they've made one that was able to last for a couple of seconds, but not long enough for it to be sustainable to produce our energy. So we still stick with fission in terms of producing a lot of our energy. So let's look at the different types of nuclear radiation that are going to be given off. These are those particles or energy that are given off whenever a reaction goes through fission or fusion. Most of the time we are going to be dealing with fission. That's the more common one for us. So nuclear radiation is charged particles and energy that are emitted from the nuclei of radioisotopes. Generally, it's given from the nuclei. We can also get rid of electrons and stuff, but we tend to get rid of those protons, neutrons, and things like that. There are three different types of nuclear radiation that we're going to talk about. We're going to talk about alpha particles, beta particles, and gamma rays. Alpha and beta are the two more common ones that we're going to use and come across. So let's look at what these actual particles are and what we're going to be doing with them. So first thing that can occur is a substance can go through alpha decay. Whenever it goes through alpha decay, that means it gives off an alpha particle. An alpha particle is a positively charged particle made up of 2 protons and 2 neutrons, which is the same thing as a helium nucleus. So you need to know the symbol for each type of decay. So alpha particle symbol in the AZX form is that 4,2He. So it has a mass number of 4, atomic number of 2, and it's that helium nucleus. Alpha, you'll also see represented as a lowercase Greek alpha, which looks like an A. Sometimes you'll see it drawn, it looks more like a fish almost, is going to be our alpha. And nuclear reactions can be expressed as a chemical reaction. So we can look at the substance we're starting with, and then when it gives off an alpha particle, what does it change into? Writing nuclear reactions is something you're going to have to be able to do. So we're going to go over this together. So here, the example we have is that we can go through the alpha decay of uranium-238. The uranium-238 is our starting particle. So 238, remember, is our mass number. Uranium is the letter U, and that is numbered 92 on the periodic table. So remember, our atomic number goes on the bottom. When it goes through alpha decay, it means it produces or gives off that alpha particle. So this will split, producing that alpha particle, that 4,2He. And then we have to figure out what else does it turn into. Now, we haven't talked about chemical reactions yet, but one thing with chemical reactions is matter is not created or destroyed. Whatever we have on one side of the reaction, we need to have that exact same amount on the other side of the reaction. So we want our mass number total on both sides of the reaction to be equal. We also want our atomic number total on both sides of the reaction to be equal. So let's look at our mass numbers. We have on the left 238, meaning on the right, our mass numbers need to add up to equal 238. So we're looking at what plus 4 gives us 238. So this unknown mass number has to be 234. We have to do the same thing for the atomic number. We're looking at what plus 2 gives us 92. So this atomic number has to be 90. And if we look, element 90 is thorium, which is TH. So we're trying to fill in what is that mass number, atomic number, and symbol for what the new atom would be in its new identity. And we're going to do several examples with these, and then you can practice them on your homework. So alpha particles are the weakest of all types of radiation. They're the least penetrating type of nuclear radiation. So they do not go very deep into your skin or into your cells. Alpha particles can travel a few centimeters in air, and they can be stopped by something as simple as a piece of paper or a piece of clothing. So these are some of the ones that we do get from the sun. We get ultraviolet alpha rays. As long as you are clothed, have something on you, it is blocking those alpha rays. Even really cheap sunblock can block these alpha rays and things like that. All right, so let's look at beta decay. This means that we're giving off a beta particle. A beta particle is an electron that is emitted or given off by an unstable nucleus. So the nucleus is actually like repelling those electrons essentially. Beta particles you're going to see in the AZX form. Since it's an electron, it has no mass. So the top number is 0. It has a charge of -1. So the atomic number we assign to be -1. And electrons are that lowercase e. This is also written by a lowercase beta, which looks like a bee with a tail at the bottom. So with beta particles, the atomic number is -1 and mass number is 0. So mass stays the same, but the atomic number will change. Beta particles are a lot smaller than alpha particles. So due to their smaller mass and faster speed, beta particles are more penetrating than alpha particles. They're more dangerous than alpha particles. These can pass through paper and clothing, but they can be stopped by a piece of metal. So these are going to be able to penetrate through your skin and into your cells more than an alpha ray would. And to look at these reactions, I have the example of we're going through the beta decay of thorium-234. So yet again, when it is written out, we look at what our original substance is, the thorium-234. Just remember, 234 is our top number. Thorium is number 90 on the periodic table, and it has the symbol of TH. It's going through beta decay, meaning it gives off that beta particle, the 1 or 0 -1e. And we're looking at what is left over after it gives off that beta particle. I will tell you, if you miss one balancing it, it will be a beta. Beta tends to trip people up when they're finding the atomic number, especially. So let's find our mass number, our atomic number, and our symbol. So looking at mass number first, on the left, our mass number is 234. So on the right, our mass number also needs to be 234. So we look at what plus 0 gives us 234. So remember we said the mass does not change. So that mass number stays 234. Where people mess up is that atomic number. So thorium's atomic number on the left is 90. On the right, we have a -1 and then our unknown. So we have to look at what plus -1 gives us 90. And this one will be 91, which is proactinium, which is Pa. So like I said, be careful when you are balancing beta, because people tend to do like 90 minus 1 versus what plus -1 equals 90. They tend to kind of do the math a little backwards. All right, and then let's look at gamma decay. Gamma decay simply gives off a gamma ray or a ray of energy. So a gamma ray is a penetrating ray of energy emitted by an unstable nucleus. Gamma rays have no mass and no charge. So a lot of times you'll see them written as 0, 0, and the symbol for gamma, it's like a V with a tail at the bottom. And these are similar to X-rays and visible light that simply move through space and move at the speed of light. So it is just a type of energy instead of a particle itself. Gamma rays are much more penetrating. They are much more dangerous than alpha or beta. It actually takes several centimeters of lead or meters of concrete to stop gamma radiation. So gamma radiation is the stuff that's given off by bombs and things like that. That have that tremendous amount of energy, lots of heat. Those are going to be gamma rays. So with gamma rays, the atomic and mass numbers stay the same. It just releases energy. A lot of times we do not deal with gamma rays. If we do, they tend to be coupled or paired with an alpha decay or a beta decay. So in the process of alpha or beta decay, it gives off a gamma ray. So you'll see our reaction from the previous slide down below, where we have the thorium-234 getting rid of that beta particle, producing proactinium-234, and also giving off a gamma ray, giving off energy when this occurs. All right, so just to show you that alpha particle is the largest one, it's the least penetrating, so the least dangerous. Beta particles are smaller, so they can penetrate further. Gamma rays aren't an actual particle, it's just energy, and that energy can move through those thinner materials. So let's do a couple more examples just for good measure. So here it wants us to write a balanced nuclear equation for the alpha decay of polonium-210. So remember, we start with whatever we're given. So polonium-210, 210 is our top number. Polonium is number 84 on your periodic table with the symbol of Po. Says it goes through alpha decay. So it gives off that alpha particle, which was the helium nucleus, the 42He. And we're looking at what it makes whenever it gives off that alpha particle. So remember, we're looking for our mass number up top. We have to look at what plus 4 gives us 210. So that would be 206. Looking at our atomic number on the bottom, we're looking at what plus 2 gives us 84. Well, that is 82. And if we look on our periodic table, number 82 is lead, which is Pb. And beware, because some of the elements, the symbols don't match with their English name. And people tend to kind of start making up their own symbols. If you do not know what the symbol for an element is, or even if there's some doubt and you're unsure, look it up on the periodic table. I can't tell you how many times someone misses points on a question because they use the wrong symbol, because they just kind of made it up on their own. Let's look at the next one. Here we have read a balanced nuclear equation for the beta decay of carbon-14. So yet again, we start with whatever particle is given. The 14 is our top number. Carbon is number 6 on the periodic table, and it is C. It goes through beta decay. So it gives off that beta particle, that electron, which is the 0, -1e. And we're looking at what else does it form. So look at your mass number first. We have what plus 0 gives us 14. So remember that mass stays the same. The atomic number is where it gets tricky. Remember, we're looking at what plus -1 gives us 6, with meaning this would be 7. And number 7 on the periodic table is nitrogen, which is N. So that makes a particle of nitrogen 14. All right, so we talked about most of our radiation we're exposed to is that background radiation. But whenever nuclear radiation exceeds those background levels, that's when they can actually start to damage your body by affecting your cells and your tissues of the body. So all types of nuclear radiation ionizes atoms. So it alters the atom itself whenever it is radioactive. So the bonds holding proteins and DNA together can actually break to cause the cell not function properly. So it essentially fries the veins where blood is not going to circulate through properly. Or it is possible where maybe a cell is replicating uncontrolled and things like that. Alpha, beta, and gamma radiation are all types of ionizing radiation. Like you said, alpha tends to be the weakest. Alpha particles can cause burns, but tend to not do harm unless they're inhaled or ingested. So you're exposed to alpha rays daily from the sun. And they're not really going to affect you unless you're ingesting it or swallowing it. Beta particles, remember, are smaller, so they're more dangerous. They can penetrate tissues and do damage. So these are our beta rays. You also get these from the sun. These are the ones that can start to cause melanoma and stuff like that whenever you have that chronic sun exposure. And then we have gamma rays. These, like we said, are the most dangerous. They penetrate deeply, exposing all organs to damage. So like I said, these tend to be in nuclear warheads and things like that. When people are exposed to gamma rays, that's when they can actually get radiation poisoning, and their body and their organs start to slowly break down over time. All right, and that is where we are stopping today. You can go through the part of the homework on nuclear decay. It has practicing balancing out those equations and writing out those equations. I will tell you, not every atom is going to be radioactive. The ones that are radioactive all the time, we'll talk about tomorrow a little bit more. But those are the transuranium elements. So anything from uranium up, which is 92 and up, is radioactive and will break down. So utilize your time wisely, practice writing out and balancing these equations. That is something that you will definitely see come up on an assessment.